Hello, everybody. Welcome back. Today we're going to be looking at Unit 7.9, which is the Introduction to Le Chatelier's Principle. Now, because I've done my videos a little bit out of order, I've actually already covered Unit 7.10, which also talks about Le Chatelier's Principle, and I gave you a little bit of an introduction there, so we're really covering the meat of Le Chatelier's Principle in this lesson. I like to do 7.10 before this one. So that's what we're going to be talking about today. So let's get started. So as I said, we have already talked about Le Chatelier's Principle a little bit already. When we talked about calculating Q and when Q is different from K, what happens, what kind of a shift is there to restore equilibrium? And that's essentially what Le Chatelier's principle says, that when you have a system at equilibrium, if there is a change to the system, or sometimes they'll use the word if there's a stress put on the system, the reaction will shift in one direction to reduce that stress or that change, and equilibrium will always be restored. So there's essentially three different ways that you can, quote, stress a system. And the first way that you can stress a system is by changing the concentration of one of the components in that chemical reaction. Okay. You could add more of a certain component, or you could remove some, okay? Just changing the concentration is essentially going to cause a shift. And you likely covered this simplified discussion of Le Chatelier's in your Chem 1 class. Essentially, ladies and gentlemen, whenever you add more of a certain component, the reaction will shift away from that added component. If you remove a component from a chemical reaction, the reaction will tend to shift toward that removed component. Okay, so just a quick example. If I were to decrease the concentration of that product by removing some of it, the reaction will, in order to restore equilibrium, the reaction will shift in the forward direction so that that removed product is built back up. So we'll be consuming some of the reactants and producing more product. Whereas, let's say I added more, I increased the concentration of SCN minus, the reaction would shift away from that added component in the forward direction to consume some of that added reactant and produce more products. Notice I am not just saying shift right, shift left, because you can't say that, so neither can I. Okay, and we've actually already talked a little bit about this. You know, when you change the molarities, you can calculate Q, that reaction quotient, and based on whether Q is less than or greater than K, you can determine which direction the shift is going to occur. All right, but let's look at this in a more visual way on a graph. Okay, and I'm going to use the same example where I'm going to be adding more SCN minus. I'm going to be increasing its concentration. Okay, so I want you to look at this graph, and this may look kind of complex, but I promise you it is not nearly as complex as you think. So in this first section, from here to here, okay, you'll notice that the concentrations of all the components are remaining constant. We are at equilibrium. But then what happens? There's a stress, and there it is. What was the stress? We increased the concentration of SCN minus. Okay, now the other two we did not change at first. All we've done is add more SCN minus. That is, and I'll even write it down, that is our stress right there. And I'll tell you guys, Le Chatelier questions on the AP exam are usually not just going to ask you, which direction will this shift? They're going to ask you questions about not only that, but what happens to the other components of this reaction as a result of this shift. Like, for example, they might say, additional SCN minus is added. As a result of that, what happens to the molarity of the other reactant, Fe3 plus? As this reaction restores equilibrium, what's going to happen to the concentration of this guy? They might ask you something like that. So let's look at it. If we add more reactant, we said on the previous slide, we know the reaction is going to shift in the forward direction so that some of that added reactant is consumed and more product is made. And look at what happens to the molarities of all of these things. The molarity of the product increased, and that's what should happen. If we're going to be shifting in the forward direction, the product, we will be getting more product. But look what happens to both reactants. Shouldn't be a surprise to you. If we're shifting in the forward direction, remember what I said, these reactants will be consumed. That means their molarities will decrease. Okay? And then at this point, you'll notice that the molarities flatten out again. Equilibrium has been re-established. Now, is the equilibrium at the same molarities it was before? No, but equilibrium will always be re-established. Okay, so this is just a graphical way to look at Le Chatelier's principle. Let's look at another one. Same reaction, but this time here is the stress. I'm going to add OH minus, the hydroxide ion. And you might say, well, wait a second. Hydroxide isn't even in that reaction. And this is another thing that's common on the AP exam. If a question has you adding more of something that's not even in the reaction, chances are that added thing is going to react with something in the reaction in front of you. And look at what it says in green. We're going to add hydroxide ion, which creates iron hydroxide precipitate. Okay, that would not be something you'd be expected to know, I don't think, because that's one of the solubility rules that is not one of the first two that you need to memorize. But if OH minus is going to react with the iron ion, that very first reactant, to create this precipitate, here's sort of the net result of that. It's essentially like removing the iron ion out of this situation. So our stress is really that we are decreasing the molarity of the iron ion because it's reacting with this added component. So imagine if we are taking this reactant away, we're decreasing its amount. Think about which direction is that going to shift? When you lower the molarity of some component or you take it out, the reaction is going to shift toward that removed component. So let's look at this graphically. All right. So once again, all right, in this area here, we are at happy little equilibrium. But then what happens? We add OH minus, and as we said, that is going to react with that iron ion, the first reactant, and here's our stress right there. The amount of the iron ion is going to drop, okay? Because it's going to react with that hydroxide. So let's think about what's going to happen here, all right? In response to that iron ion being removed, the reaction is going to shift in the reverse direction so that we can build back up the levels of reactant. We'll be creating more reactant and using up, consuming some of the product. So look at what happens to each of these components. The molarity of the product drops, and it should. We're shifting away from it. The two reactants, their molarities go up because we are shifting toward them. Okay, so that should not be unexpected. And then again, once again, equilibrium gets reestablished. It's at new molarities, but equilibrium will always be reestablished. So the reason that I'm showing this to you is because, as I said, Le Chatelier problems very often will not just ask you to identify the direction of the shift, but also they're going to ask you what happens to the molarities of some of the other components of the reaction. Do they increase? Do they decrease? And you need to be able to answer that. Okay. Last thing that might happen that affects concentration is what if you dilute or concentrate these solutions? And this can be a little bit tricky. All right, so let's think about the fact that, for this particular reaction, this is what the equilibrium expression would look like. All right, so let's imagine that to this happy little equilibrium system, we pour in some water into the beaker where this reaction is taking place. If I dilute this situation, that is going to cause all of the molarities, not just one of them, but all of the molarities of all the components to decrease. Okay, and think about that. Whoops, let me change colors so you can see it. The product molarity is going to go down, and so are both of the reactants. Okay, the numerator is going to decrease, but so is the denominator. And here's the key, guys. I'm no longer at equilibrium because I've changed the system. Because there's two aqueous components in the denominator as opposed to just one in the numerator, there's going to be a bigger effect in the denominator. So think about it. Think about a fraction. If the denominator gets smaller and like more so than the numerator, that's going to cause Q to become a larger number. Okay, in that particular case, Q is going to become greater than K. Okay, think about it. If you put a really small number in the denominator, that makes the result of the fraction, the quotient of that fraction, larger. And let's remember what happens. When Q is greater than K, what happens? The reaction would, and let's just refresh our memories here, we are diluting this in this example. Okay, when Q is greater than K, the reaction will shift in the reverse direction to form more reactant and consume some of that product. Okay, so in general, if you dilute a chemical reaction, the reaction will, in response to that stress, will shift toward whichever side has more aqueous components. In this particular case, the reactant side had more aqueous components, so we're going to shift in that direction. If you were to concentrate the solution, okay, and how might that come about? Well, let's say we have this reaction going on in a beaker and we leave the beaker out on the counter for a week, and some of the water, the solvent, evaporates. Well, that's going to make all of the molarities go up, and we're going to see the exact opposite of what we just talked about. Okay, so when you dilute or concentrate something, all of the aqueous components are affected, and so you've got to think about which part is affected more, the numerator or the denominator, and what is that going to mean for your Q value. So what I want you to do is take a look at this question, and I'm going to introduce it to you, okay? But then I want you to pause the video and see if you can solve it on your own. It says, consider the following equilibrium system, and we're given a balanced equation. Evaluate each stress to determine if it will result in an increase or decrease in the concentration of chromate ion, CrO4 2-, as equilibrium is reestablished. Okay, so let me just make sure you understand what you're doing here. Here's the chromate ion. For each of these stresses, A, B, C, what I would do first is determine which direction it's going to shift. Okay, and then based on that decision, is chromate, which is a product, will that ion, will its molarity be increasing or decreasing based on your decision on which direction it's going to shift? Okay, so pause the video, see how you do. All right, let's take one stress at a time. Okay, so the first stress says we are going to add some of the dichromate ion, which is our very first reactant on the left-hand side. So in your mind, I want you to think, okay, which way is this going to go? I've got an added component on the left, a reactant. That's going to cause a shift in the forward direction to consume some of those added reactants and produce more product. And we were asked, what's going to happen to one of those products specifically, the chromate ion? So here's what I said. Okay, first of all, you guys, you got to answer the question. The concentration of the chromate ion will increase. But then you always have to defend your answer. So what did I say? I said the additional dichromate ion will cause Q to be less than K, and the reaction will shift to consume some of this additional reactant and create more product. And of course, the chromate ion that they asked us about is one of those products. Please notice, guys, that I did not say anywhere in here, shift right, okay? You can certainly think that in your mind, okay, this is going to shift to the right, but you don't ever want to put that on a test or on the AP exam, okay? You want to say the reaction will shift in the forward direction. That's okay, but you also got to say a little bit more, will shift to consume reactant and create more product. Okay, let's look at the next one. It says addition of hydroxide ion. Again, that ion is nowhere in this reaction, but look what it says. The ion will react with the H3O plus ion, and that is in this reaction. So remember what we did this a similar example. OH minus is going to react with that H3O plus, so it's essentially like removing H3O plus from the situation. So if you remove one of your products, which way is it going to shift? It's going to shift in the forward direction to build up the levels of those products and consume some of the reactants. So what did I say? I said the concentration of the chromate ion will increase again. So I've answered the question, but then I've got to defend my answer. The OH minus will react with the H3O plus, and the reaction will shift to replace the H3O plus ion by consuming reactants and creating more products. Nowhere have I said shift right, okay? You can think it in your mind, but don't say it. Okay? All right, last one. We concentrated the solution by allowing some of the water to evaporate. If that were to happen, that would cause the molarities of all of the aqueous components to increase. Okay, so what is that going to do? That's going to have a bigger effect on the product side because there's more aqueous components on the product side than the reactant side. Okay, so let's see. The concentration of the chromate this time will decrease. And why? All molarity values will increase as solute volume decreases. As the water evaporates, all the molarity values are going to go up. The increase in molarity on the product side will be greater because there are more aqueous species. The reaction will shift to consume products and form more reactants. I did not say shift left, even though that is actually what's happening. Okay, but you can't say that. All right, so these are the kinds of Le Chatelier's questions you're going to see in free response. Okay, before we move on to the next possible stress that you can see, I just want to say one thing before we move on. If you were to change the amount of water in this particular example right there, guess what? There would be no shift, no change. Remember, guys, what states of matter are included in an equilibrium expression? Gases and aqueous components. What things are excluded from equilibrium expressions? Solids and liquids. So guess what? Making changes to a liquid or a solid component of a reaction will have no effect, no shift whatsoever. Don't fall for it, okay? Something else that also has no effect would be an added catalyst. All right, if a question ever says you have this happy little equilibrium system and a catalyst is added, which of course we know speeds up a reaction, the rate of reaction, no shift, okay? No effect in terms of Le Chatelier's principle. All right, so I just wanted to call your attention to that. Okay. The second type of stress that you can put on a system is not changing concentrations, but changing the pressure, okay, of the system. All right. And if you all will recall, pressure is a word we only ever used when we were talking about gases. So this particular stress is only ever going to affect gases in a particular reaction. Sometimes the question will be very direct and will say, you know, the overall pressure of the system is increased or decreased. Sometimes, like in letter C, they'll be a little more crafty about it, and they'll say things like, the volume of the container is expanded. Well, remember Boyle's law, if volume increases, that means pressure decreases, and then you can refer back to letter A. And we're going to talk about what happens when you change the pressure. And I'll come back and talk about letter B in just a second. So let's look at some examples. All right, I want you to focus your attention on this first reaction at the top. Let's say we increase the pressure of the system. Well, on the previous slide, it says if you increase the pressure, the reaction will shift to the side, listen carefully, it will shift towards the side with fewer moles of gas in order to restore equilibrium. Well, how are you supposed to know how many moles of gas there are? I don't see any numbers there. Okay, there's no information given to me other than the reaction. Well, we're going to focus our attention on the coefficients. Okay, they're all 1, 1, 1. Okay, so let's say again, let's say that our stress is we are going to increase the pressure of that first reaction. So according to the rule, it's going to shift to the side with fewer moles of gas. Ladies and gentlemen, look at the coefficients. They're all, first of all, these are all gases. On the reactant side, there are 2 moles of gas. On the product side, there is only 1 mole of gas. So if we were to raise the pressure of this first reaction, the reaction will shift in the forward direction to consume reactants and produce more products. Okay? If the pressure were to decrease, then it's the opposite. If you decrease pressure, you will shift to the side with more moles of gas. So if we were to decrease the pressure, this particular reaction would shift in the reverse direction to create more reactant and consume product. Okay? Now, I have a cutesy little way to remember this rule about what happens if you increase pressure, what happens, okay? So many students in high school that take AP Chem are 11th graders, juniors, and that tends to be a year in high school where you feel a lot of pressure on you, okay? You're taking some of the hardest classes. It's one of the most stressful years of high school typically. So I say that my juniors are feeling under high pressure, okay? Now you may be different, but this is just me. When I am feeling like I'm under a lot of pressure, you know, in my work or in my life or whatever, I tend to want to not be around big crowds of people. Like I'm not going to head out to a party when I'm feeling really pressured and stressed. So when I'm under high pressure, I want to go to places where there are fewer people. High pressure, fewer moles. Okay, it's just my cutesy little way to remember that, okay? Whereas when I'm feeling under low pressure, you know, and I'm feeling good and I'm feeling relaxed and I don't have any pressure on me from work or anything like that, that's the time that I want to go to a party where there's lots of people. So when I'm under low pressure, I want to go to the places where there are more people. Low pressure, more moles of gas. It's just my little way of remembering that trick. Use it or don't, it's up to you. Okay, look at the middle situation. Okay, everything is a gas, and that's good. Okay, we'll look at an example of when something isn't all a gas. And let's say this situation, I'm going to throw you a little bit of a curveball. So we're looking at this middle equation here. Let's say I increase the volume of this container. Remember Boyle's law. What's that going to do? If the volume goes up, that's going to cause the pressure to go down. Remember the little trick to remember this. If I'm under low pressure, I want to go to the side with more moles of gas. So look at this middle equation. Look at the coefficients. How many moles of gas are on the reactant side? 4 moles. How many moles of gas are on the product side? 4 moles. Equal number of moles of gas. Guess what? Changing the volume or the pressure in this particular example will have no effect. There will not be a shift because there are equal moles of gas. Okay, look at the last one. Remember, changes in pressure only affect gases. So let's say we increase the pressure of this reaction here, how many moles of gas are on the left-hand side? 6 moles. How many moles of gas are on the right side? 0. So if I were to raise the pressure, think about the rule, we shift to the side where there are fewer moles of gas. So I will shift in the forward direction to consume reactants and produce more products. Okay? So we have looked at changes in concentration, changes in pressure. Okay? The last thing I want to say about pressure in gases, occasionally, let me go back one slide here, you will see an addition of an inert gas in a problem. This word inert just means unreactive. It doesn't do anything, okay? Like, for example, look at this first reaction here. Let's say that to this reaction, helium gas was added to this equilibrium system. Well, helium isn't even in this reaction, nor is it going to react with anything. It's inert. Guess what? No effect. Maybe that helium is acting as a catalyst or something, but as we said before, catalysts have no effect. So if you ever see this word inert, an inert gas is added, don't let it freak you out. No effect. Okay, third and final stress. Changing the temperature, okay? Not only is it going to cause a shift, but ladies and gentlemen, temperature changes also will affect the value of K. Remember, this is the only thing that can change the value of K. Changing the molarity, changing the pressure is not going to affect the value of K. Temperature will, however. So let's look at an endothermic situation first. So I've got this example reaction here. I know that this reaction is endothermic because the delta H value, this is a little bit of review, going back a couple of units, the delta H value is positive. That tells me this is endothermic. And what I would recommend, okay, let me put a few things up here and then I'm going to write this in. If you're dealing with an endothermic reaction, that means heat is treated like a reactant. So I'm going to write the word heat or energy on the reactant side. And guys, we're going to treat heat just like it's any other component of this reaction. So let's imagine that we are going to raise the temperature of this reaction. What is going to happen? Well, if you raise the temperature, that's like adding more heat. And heat, because this is endothermic, is treated like a reactant. So what's going to happen? This reaction is going to shift in the forward direction to consume some of that heat, that added reactant component, and produce more products. And as I said, temperature is going to affect the value of K. So what is going to happen? Is K going to get bigger or larger? Remember that K is products over reactants. And look at what's happening. We've said that this is going to be shifting in the forward direction so that more products are made, more products, and some of those reactants are consumed. So there will be more products than reactants. This will result in a K value that is larger than it was before. Okay, so you can't answer that question until you've decided which direction the reaction is going to shift. Okay, so let's look at the opposite situation. All right, what happens if we decrease the temperature? Okay, well, it's still an endothermic reaction. Heat is still a reactant, but if you lower the temperature, that's kind of like taking heat away. And heat is still a reactant, treated like a reactant. If you remove something on the reactant side, the reaction is going to shift toward that removed component. It will shift in the reverse direction to create more reactant and consume some of the product. So my amount of product is going to go down, and I'm going to get lots more reactant. So K is going to become smaller than it was before. Okay, so usually they'll ask you, what will happen to the K value? Will it increase or decrease? Okay, you can't answer these Le Chatelier questions in relation to stresses, changes of temperature, unless you know whether it's endo or exo, and you will always be told that information. So what if it's exo? All right, I know that it's exo because the delta H value is negative, and if it's exothermic, I'm going to write the word heat on the product side. So this time, if I raise the temperature, that's like adding more heat. It's going to shift in the reverse direction. Okay, let's remember products over reactants. That's going to consume some of my products, use some of them up, and create more reactant. So K is going to, in this particular situation, K is going to decrease. That fraction is going to become smaller. Okay, so what if we, last example, what if we lower the temperature? That's like taking heat away. The reaction is going to shift towards that removed component. We're going to make more product and use up some of that reactant, so the K value is going to go up. Again, I could not have predicted these shifts without knowing that the reaction is endo or exothermic. Okay, so this one is very straightforward here. Okay, you're given a reaction, you're given a delta H value. It says, does the equilibrium constant for the reaction shown increase or decrease when the temperature of the system is increased? Okay, so this should be pretty straightforward, but I want you to pause the video and see if you can do it. All right, so I see that this reaction has a negative delta H value. That tells me this is an exothermic reaction. I am just in the habit, I tend to write in the word heat into the reaction on the appropriate side. In this case, heat should be on the product side. If we raise the temperature, here's what's going to happen. Okay. I've said that the value of K will decrease, and here's my reasoning. The forward reaction is exothermic. You need to state that. Therefore, an increase in heat, we're raising the temperature, increase in heat will cause the reaction to shift in the reverse direction, creating more reactant and consuming product. If you wanted to, you could add a little bit more detail when you say creating more reactant. You could maybe put in parentheses, increasing the denominator of the K expression, and consuming product. You could put in parentheses, decreasing the numerator of the K constant. Okay, you could add that if you wanted to. So that one should have been pretty straightforward. This is a, oh, I had more. Oh, there, I added that. With the numerator of the K expression products decreasing and the denominator of the reactants increasing, the overall K value will be less than it was. Okay, well, there we go. Okay, so that's a complete answer right there. I have one more problem that I want you to try. This is a multiple choice, but it's a tricky one. So I want you to see if you can figure this one out. All right, so the question says, which experimental conditions would result in the greatest production of dinitrogen tetroxide? All right, so let's imagine you are a factory owner and your whole job is to produce N2O4. Okay, well, this is the reaction that your plant is using to create your product. And you're a business person, you know, you want to get the most bang for your buck, okay? So do you want to keep your factory at high temperatures or low temperatures? Do you want to keep the pressure inside the vessel where you're doing this reaction? Do you want to keep that high or low? What's going to make you get the most product? So let's look at it. All right, so first of all, I can see that this is exothermic. So I'm going to write in heat on the product side. Our goal, ladies and gentlemen, we want this reaction to be shifting as much as possible in the forward direction. So let's take it one piece at a time. What do we want the temperature to be doing? What should be happening to this heat if I want the reaction to shift in the forward direction? Do I want to be adding more heat or taking heat away? Hopefully you said taking heat out. If I'm constantly taking heat away from this reaction, because heat is on the product side, it's treated like a product, that will cause the reaction to shift in the forward direction. So I want to keep my factory nice and cold. I do not want my factory to be warm. I want it cold. That's going to cause a shift in the forward direction. So let's think about pressure. Both of the components of this reaction are gases. 2 moles of gas on the left, 1 mole of gas on the right. Remember what we want. We want the reaction shifting in the forward direction. We want it shifting towards the side with fewer moles of gas. What kind of stress does that? High pressure. So there's my answer. I want to keep my factory at low temperatures and I want it at high pressure. And this is a real thing. You know, this is something that chemical manufacturing plants have to think about. If they are making N2O4, they don't want to build their factories, you know, in Brazil that's on the equator, all right, because they're going to have to run their air conditioning and their freezer units like crazy. It makes more business sense to build those factories in colder climates. Okay, so sometimes chemistry and business intersect a little bit. All right, but that's a kind of question you could see that involves Le Chatelier in a more multiple choice kind of setting. Okay, I know that was a lot, okay, and it's a lot of concept. It's a lot to wrap your brain around. But Le Chatelier is a very, very important concept. And let me just say again, please, please, please don't say shift right, shift left. You can't say that. You got to give a little bit more detail than that. And you certainly have to give reasoning as to why that's happening. Okay. So I hope you have learned not just a little something, a lot of something. And I look forward to seeing you next time.